Okay, so for today, we are supposed to create our queue of tokens, right, for strings. Okay, so we have our function or procedure. So this guy is going to, or an expression, I guess. This guy is going to look something like this. I know some of you asked, can you have it like this and then tokenize on spaces? That's okay if you did it that way. We're going to write it today to tokenize on anything that we pass in this second collection of ops. All right. And then what we're going to do is we're going to give them the option to keep these ops or not. So kind of give ourselves a power tool in our string factory split. So we can say, well, I just want the 123, the 42, the 8, and the 2. Or do I want the 123 and the plus sign and the 42 and the minus and the 8 and the times of the 2? So the logic is not a substantial difference. So I'll go into string factory here and we're going to take in a, does bool exist yet? So bool, you know what? Let's not ask that question yet. We'll just keep it close to what the assignment was. All right, so we're going to take in our string, we're going to take on our delimiters, and we're just going to, for right now, presume that we want to keep all the operators as well, the delimiters. Okay, because that's what we're going to need in our input queue for our shunting yard. Okay, so, and I'll just go ahead and copy these couple of things over here inside of comments just so we have them to reference off of. Oh, that's interesting that it kills it like that. All right, good enough. All right, so this is kind of what our, like an example of what our inputs might look like. And ultimately, we need to load these guys into a queue. So we need to go ahead and write our queue real quick. So here's our queue HPP. All right, and our queue is going to have a couple of private fields and then a couple of public things. So private fields, we're going to keep track of a node pointer called head. And we're also, and I need to import or include node HPP. So we're going to keep track of a node pointer head. I'm also going to keep track of a node pointer tail. All right, because it's going to be for a queue, we need to be able to enqueue, adding to the end of the linked list, and to dequeue, removing from the front. So keeping track of both the head and the tail can be beneficial things here. All right, we're going to need our constructor here for queue. That'll take in no parameters. And then we want to add our function for void enqueue, which will take in an int payload. And then we're going to have an int. And actually, in this case, the things we're holding inside of our queue is not integers anymore. We're now holding strings. So we'll take in a string payload. And we'll take in a, so this guy will return a string, dequeue, remove from the front. All right, so those are the functions that exist for our queue. So I'll go into our QCPP. And we also might just decide whether it's helpful or not to keep track of a count. And we will include QHPP. And we'll go ahead and write these things. All right, so when we initialize our Q, we're going to go ahead and set this head equal to 0, this tail equal to 0, and this count equal to 0, which is funny because these first two zeros mean nothingness. This guy means actually a count of 0. All right, so then NQ means we're putting something at the end of the Q. So we'll ask the question if, well, we know that tail is going to ultimately point to this. So we're going to ask the question if this tail, if that guy already exists, then we're going to have to update the tail. In any case, we need to create ourselves a new node. And let's go peek at node real quick and make sure our nodes are strings, not ints. Yep, our node is a string payload. So we wrote our node correctly. All right, so we'll say node pointer, we call n, I guess, is equal to a new node passing it our payload. Then we'll ask the question if this tail is a thing, then what we're going to do is we're going to go ahead and say this tail dot set next node. And the reason we have to do the arrow here is the tail is a pointer. So it's this is a pointer. So to resolve it and say a dot, we go to tail. Tail's a pointer. To resolve it and say a dot, we do the arrow. So we're setting the next node to the new node we just created. And then we'll update tail to be equal to the node we just made. That's if tail already is something. And if tail is already something, then we know head is already something. Else, if tail is not already something, then what we need to do is we need to make head and tail both point to this new guy. We have the empty list, right? So we'll say this dot head is equal to n, this dot tail is equal to n. So this is if we currently had the empty list and we go ahead, or the empty queue in this case, and we just make the head and tail both point to that one guy we just added. From that point forward, we differentiate tail from head. Okay, and any way you cut it, we'll say this count plus plus, because we just added something to our queue. So that's NQ. For DQ, we are removing something from the front. We can, I guess we can presume that we are, since we're not doing error checking yet, we can presume we're not DQing off the empty list. So I guess we can just ask the question if this head, if that's a thing, then what we want to do is we want to create our node pointer temp, and this is going to be equal to head. So remember the front of the list right now. Then we'll say this head is equal to this head get next node. So we'll make head point to his own next node after we've preserved the original value of head. And then we can go ahead and we want to make sure we clean up memory appropriately. We would do something like int val to return is equal to temp get payload. Then we can say delete temp. Oh, inside of our node, our get payload looks like it is, oh, it's a string there. It's a string there. Oh, my error is inside of Q. I am working with strings here, not ints. So temp's payload is a string, so that's the value I'm going to return. Then I'll go ahead, and now that I've preserved that value, I can delete the memory for temp. This is just us cleaning up our own mess. And now I can go ahead and return val to return. So this guy will return the string that is at the front of the list. And we're only going to do that if this head is a thing. Now, if we're doing stuff like that, though, we also need to say this count minus minus. If we do actually remove something, we need to decrement our count.
Just for clarification, you also could have, rather than saying delete temp, you could have just set temp equal to 0, right?
I think technically no, because setting it equal to 0 gives it a null value, but that does not get rid of the memory that used to be there. Because temp points to a real place in memory that really has a node there. If you overwrite temp with a 0, now you're making temp no longer point to that place in memory, but that place in memory still exists. It's still there, and it still has a node there. We just have no way of getting it there. So now it's like permanently lost with wasted memory.
Okay.
Okay, so we'll do this. Now, I need to remember, does C++ enforce that we return a value? Let me just do a quick compile here. It does not. Good. That allows us to be conveniently lazy without error checking right now. All right, so we're only going to do anything here if we have a real value. I suppose we could do something like a, you know, else, I don't know, return the empty string or something like that. Maybe we should say this should never happen. Throw an exception, but I don't want to deal with exceptions yet. All right, so we probably want to have some sort of error message come off of our DQ in this case, so we'll just kind of put a little placeholder thing here there for that. And let's make sure that double quote counts as a, it does. I wanted to make sure that counts as a standard string literal. All right, so there is DQ, NQ, and there's RQ. So we should have something that can hold some things. Just for real quickly, let me go ahead and create a void display just so we can test our Q real quick. Check to make sure I put a semicolon here. I did. All right, so we're going to say, well, here we'll just say node pointer cur node is equal to this head while cur node is a thing. We will do a cout kernode get payload. And then we'll throw a little space after that for right now. And then we'll say kernode is equal to kernode get next node. And then when we finally bail out, we'll just do a cout \n. So now a queue should be able to display itself. So let's just real quick enqueue a bunch of things inside of driver just to make sure our queue is doing what we want it to do, that we can trust it. So I'll just, let me just comment these things out for a second.
Question?
Go ahead.
It seems like this can do all the things that Q can. Is there any particular reason why we're not using linked list?
Well, yeah, queues are substantially simpler. So, I mean, if you already have a linked list that knows how to deal with strings, then you could just use that for all the heavy lifting. Think of that as being, you know, you need to do some small job in the at the construction site, but you bring in some huge bulldozer that knows how to do 40 different things to do those two things. Where a queue knows how to do two things. It knows how to enqueue and it knows how to dequeue. That's what a queue knows how to do. Where a linked list knows how to add front, it knows how to add end, remove front, remove end, add it middle, add it, add an index, remove an index, and you can add a whole bunch of other stuff to linked lists. So linked lists would be like that bulldozer that is like overkill for the project. Not that you couldn't use it for solving this problem. But if we want to start conceiving of problems in terms of what's the right tool for the job, in this case, when we're thinking about shunting yard, our input queue is a queue. It can do two things. You can enqueue and you can dequeue. Our output queue is a queue. You can do two things. You can enqueue and you can dequeue. Our operations stack is a stack. You can do 2.5 things. You could push, you could pop, and we'll call the half thing a peak. So those are the simplified, so a queue and a stack are simplified versions of linked lists. So we're representing them, we're reinforcing this idea of what this tool actually is, what makes this guy a queue versus what makes something else a stack versus a much more general purpose linked list that we can use in all sorts of different ways, including using it like a queue or including using it like a stack. Does that make some sense?
Yeah, that makes sense.
Okay, so I'm just going to go ahead and fill our queue up with some stuff. We'll call this guy test queue, and he'll be a new queue. And then we'll say, I don't know, for int I is equal to 0, I is less than 10, I plus plus. And we'll say test queue enqueue. And we'll give it we'll say element concatenated with I. Pretty sure I can concatenate a integer onto a string in C++. I don't have to convert that guy to a string, but we will find out shortly. So this should fill up our test queue with element 0, element 1, element 2, so on and so forth. And then we'll tell our test queue to display itself. And hopefully we have a pretty queue displayed to the screen. And we do not. Have I broken how strings work, or have I made a bad assumption about how strings work? Let me do something here. Okay, so that fills it up with all the elements. So something with how my concatenation was working is breaking this. So we'll say S is equal to element S concatenated with I. String and an int. Yeah, it does not like that. So I need to do, what is it called? I to S. How do I turn an int into a string in C++?
If it's int to string,
Int
in parentheses.
int. Is it to string like this?
Yeah, I believe so.
Looks like int. That doesn't look right. Let's just look it up real quick. C++, int to string. Okay, it's just called toString. toString I. So there's our element 0, element 1, blah, blah, blah. And then let me just do one additional thing here. I want to go back and put in my string literal there. I think we already saw this, so this should still work. It was the concatenation piece that was breaking it. Yep. Okay, so it looks like we have a, actually let me, real quick, let's just make sure this works. We'll go ahead and tell, we'll do a cout test queue DQ. And then we'll do our test queue display a second time, which should have one less thing in it. So there's our 0 to 9, and then we DQ'd 0, and now we have 1 to 9. All right, so we've exhaustively tested our queue. It works perfectly. It doesn't have any bugs in it. All right, right, Clancy?
Correct.
All right, so we can go ahead and dump this now. We've tested our queue and we've taught ourselves how to convert an int to a string. I am actually surprised that I can't concatenate a an int onto a string in C++ with this new fangled string class. What if I do string, oh here, I'll just say do it in S. S is equal to the empty string plus 5. And then I do a cout S. I should get the string 5 is the belief. Yeah, it does not work. Interesting. Well, that must be why they gave us this universal toString method in the string class that just does the magic for us. Okie dokie. All right, so now we can start working with our strings here. Let me, actually, I want to test one more thing here. I'll just overwrite it. So I'm going to say S is equal to 1, 2. So then S is equal to S concatenated with the char 3 cout S. Yep. Okay. So it works with chars, just not int types. Which sounds correct because that tells us that strings are implemented as char pointers under the hood, which we would have expected. Okay, so actually that little exercise we just did is, I think, pretty important because before we can start using this tool, we got to understand the portions of the tool at the very least that we plan on using. So we wanted to make sure that we understood the concatenation piece of that and how it works in C++. Okay, so we're going to go ahead and we're going to call our split function, passing it an S like this and an ops like this. And we want to go through this guy one character at a time, building up a string until we hit an op. When we finish building up a string, we're going to enqueue it. Then we're going to enqueue our op. Then we're going to start building up a new string, so on and so forth, until we get something that has all of our ops in it, all of our tokens and our ops in it. We're making the assumption right now that we want everything. All right, so we'll go into String Factory, and we'll start off with our string temp. And this guy will start off as the empty string. He's the string that we are currently building up. All right, so now we're going to just start walking through S. Does S have a, what is that, length? And it's a method, okay. So we know we're going to have to go through every single character in temp. And if we just want to have a test case to prove to ourselves how this works real quick, again, making sure we understand the tool, I can go ahead and say for int I is equal to 0, I is less than s dot length, I plus plus, and then we'll go ahead and do a cout s, and I'm pretty sure we index it like an array. So that's kind of like char at, and we'll put a little backslash. We'll get all the individual characters from that guy. So now this should show us that we can go through every element of a string. So there's all the elements of our string. Okay, so again, before we start trying to play around with logic, make sure that we understand how this tool works. All right, and kind of putting this in the larger context of how I teach programming, this idea that programming is the skill set, the language doesn't matter. So we've worked with strings for a long time with Java. Now we're diving in and using strings in C++ and making sure we know how that guy behaves. Maybe looking at what are the little nuances of difference between C++ strings and Java strings. Okay, so we'll come into String Factory here. Temp is going to be used to build up our string as we're building it. So we'll build up the 1, then the 2, then the 3. So as long as we're not looking at something that looks like one of our operators. All right, so in order for this to work, we probably want to go ahead and have a way of detecting whether something is one of our ops, one of our delimiters. So for String Factory, I'm going to give myself a private function, because this is not something we want to necessarily expose to somebody else who's using it, but it's a tool we're going to use inside. So we're going to have a static, and I'll go ahead and make this guy a bool. This guy will be called, why don't we call this is in string. There's probably already a string function that lets us check that. I suppose we can just do a quick look on that. C++ string contains. Yeah, it looks like we have a find function inside of standard. Find takes in a string, and it tells us where it found it in that string. Well, that's fine. We can use that because if it gives us something, I'm guessing it gives us a -1. If it's not found, kind of like index of. But why don't we go ahead and write our own version of this because that's fun. So we'll just have something because that'll let us look at bools here. I think bools are implemented as 0s and 1s. So is in string, this guy will take in a string s as a parameter, and it's going to return a true if, here I want to say, the s we're searching in, so we'll call this guy, let's call this guy search string, and the char to find, something like that. We want to return true or false, whether or not it's in there. We'll give ourselves this little tool. Let's go write it real quick. All right, so we want to go through every element in search string, finding out if char to find is any of those elements in there. So for int I is equal to 0, I is less than search string dot length, I plus plus. We'll ask the question if search string at bucket I is equivalent to char to find. Then we'll go ahead and return, I think we have true. So I promise you, this guy is a 1 or a not a 0. So these are more familiar ways of handling Booleans, trues and falses, but they actually are 0s and 1s. All right, so if I found it, return true, otherwise keep looking. If I went through and I looked everywhere and I didn't find it, I'll return false. So there is my is in string. So that'll allow me to conveniently ask whether or not the current character I'm looking at is in our collection of delimiters. All right, so I know I'm going to have to go through every single string inside of S. So for every character inside of S. So int I is equal to 0. I is less than s dot length. I plus plus. This will take us on a voyage through all the individual buckets of S. Each time through, we're going to say if S at bucket I, if, what's it called, is in string, passing it delims, the thing that we're looking for, and passing it S at bucket I, if that's a true statement. If the current character we're looking at is in the string called delims, then I know I've hit a delimiter. And if I've hit a delimiter, what do I need to do? I need to tack this onto a queue. So in order to do this, we're going to have to build ourselves a queue. So we have a queue pointer, answer is equal to a new queue. So up to this point, we'll say answer enqueue temp. Then we'll say answer enqueue, the empty string concatenated with S at bucket I. So that'll be our operator. And we are assuming in this case our operators are all 1 character long. And then we'll 0 out temp so we can start collecting the next string. That's only if we just ran into one of our delimiters. If we ran into one of our delimiters, we're done collecting temp. So go ahead and enqueue it. Then grab that delimiter that we just found, which is at bucket I, because we just saw that. But turn it into a string. It's possible I could just pass it a char and it'll treat it as a string, but I'll concatenate it together with a string and That'll definitely be a string. And then I'll go ahead and empty out temp so it's ready to build out the next thing. Otherwise, if I'm not currently looking at a delimiter, then I'm going to say temp is equal to temp concatenated with S at bucket I. Build up our current token. All right, so we're going to do that for every single thing in there. Now we know when we get done with this for loop, I should have one final guy trapped inside of temp. So we'll go ahead and NQ him, because the last time through we will not have hit a delimiter. We would have been building up this too, and we would just naturally end that loop. We never actually hit one of our delimiters. So that guy's still trapped in temp, so I'll go ahead and just capture him. And then I'll go ahead and return answer. I'm going to call this guy answer Q, so that's kind of fun. We'll call this guy answer Q. Well, then I got to change it everywhere else. Interesting question. Do I have a refactor thing here? Rename symbol, answer. Yep, it does. So I changed my variable there, so I'll do it again here. Just say rename symbol. I'm going to take the L off, so it's answer Q, and then it updates all the occurrences of that guy in the current scope. So that's a nice little handy thing. From the software engineering term for that is called refactoring. Okay, so that should be my answer queue. So now if I go back to driver here, I am passing in split. I'm passing in this guy and this collection of operators. I'm expecting my input queue to come out of there. And then I'll go ahead and tell my input queue to display himself. And hopefully we have a nice split up string now in queue format. Oh no. Doesn't like my is in string. Did I forget to put that somewhere?
Oh, this is the same error I had. The previous homework.
In string, okay, it's there. And that's a private guy. And then inside a string factory, here is, oh, I forgot to put the string factory thing in front of this guy. All right.
I just have a general question kind of with this. I was getting errors when I didn't define my HPP files, and it doesn't look like you're doing that. Can you go without defining them?
What do you mean you're getting errors without defining your HPP files?
Like doing the hash if in def and then define at the top of them?
Well, right, but make sure when you compile, you're compiling all the CPP files, not just driver.
Okay.
Because if you compile all the CPP files and you notice each CPP file includes some stuff at the top of it, so that's where it's bringing in your header files. So driver is using string factory and IO stream. So those HPPs get included in the compile if you compile all of the CPP files when you run it. That allows the linker to bring it all together into an executable.
Okay.
So I guess I'd have to see where you were having your error, but you definitely need to do your includes at the top here. Is that what you're asking?
Well, I guess in the top of the HPP files that I yeah, in there, that sometimes we would do at the top of those the if in def and define, and I was just wondering when you do that and when you don't.
Oh, yeah. So that would be like in a larger project. I usually leave them out. In a larger project, if you are using multiple other people's libraries where you might have a class called something that's the same as their class. So you would say if it's not already defined, if we don't already have something called Q, let's go ahead and define our own one here. This also protects us from having a situation where I come in here into String Factory and I'm including QHPP. Well, driver also includes String Factory HPP. Well, what if I end up coming in here and doing something like include q.hpp? Right now, this is going to give me at least a warning, redefinition of class Q, where if I had that class Q set up as if not defined, it wouldn't redefine it for me. Therefore, I wouldn't have had a double definition. So this is what's happening here is String Factory, he brings in QHPP. And then also QHPP is QHPP. So technically, this guy already has defined QHPP. And then I'm asking for it again. So that's why it's yelling at me and saying, oh, you have a redefinition of this guy. Where if QHPP had the if end defined at the top of it, it would only do this stuff if it's not already defined. So it kind of polices itself.
Okay, I think that makes sense.
So what I'm kind of having to do here, which is, let's call it, I'm not sure which is the better programming practice. Probably the other way is the better programming practice. By saying the if not defined, that allows you to say, okay, well, inside of driver here, I am using Qs, so I'm going to make sure I include Q. Even though I know in this particular case, I don't have to include Q because he's actually included here. That requires me to know that he was included in there so that I get my scope for the Q class. But I'm getting it through String Factory because String Factory is the guy who actually included Q. Where if you did the if not define around all of your headers, I would be able to say include String Factory as well as include QHPP, and I would get both of those. And that would be, let's say, a nice thing. Something like that, where I wouldn't have to worry as a programmer keeping track of who imported what already. I could just say, oh, I'm using Qs in here, so at the very least, I definitely need to include q.hpp, just in case one of these other fellas hasn't already included it. So as our projects get larger, that if not defined thing probably makes more sense to put in there so that we have to do less maintenance of worrying where things are defined and things like that. In fact, if you want to see that, what's the syntax for the if and define? Show me the syntax real quick. Writing that right? That seems a little sketch to me. We'll figure it out here in a second. So now I should be able to include QHPP, which only does something here if it's not already included. Although we might get the error now on node, but let's see. Yeah, we got the previous definition of class node. So I would have to have spilled through and done the same thing with node and so on and so forth. So if I'm consistent and I do that for all of my classes, so if I do if not defined node, where's my node.h? Actually, don't I put it around everything? I think I put it around everything. That for Q as well. Q HPP, driver HPP. It's in Q, it's in string factory. I don't think you want to wrap it at that top level. Yeah.
So does if in def define it without also doing hash define?
Oh, thank you. So what is it? If n define, then you do hash define like that.
Yeah.
What's the syntax?
Then it's just string factory underscore HPP for both.
Like that.
Yeah, and I think for if in def as well.
Okay. So let me go and do that for my Q as well. Underscore HPP. Node. Oh, yeah, right. That's node. That's Q. That's string factory. I think those are all my guys in this one. I know we have an error there, but we'll check that in a second. But now you see, since I did all of that inside of driver, I can still include HPP, not having to worry about whether it's been previously included. We know it was put inside of string factory, but I can put it here because I'm using Q here. I don't have to go and search around to see if I had previously put it someplace. So this would be considered better programming practice where only, so right here I'm saying include QHPP. Here's QHPP. This is saying only if it's not already defined, should we go ahead and define it again. Does that make sense?
Yeah, so it's kind of, it can be unnecessary though. It's just, I guess it looks more laborsome then. So you could go without it. It's just maybe not best practice.
Yeah, I would say you could go without it like I was doing, but I would actually probably say that's not good programming practice. It's probably better programming practice to put it in there so that as a programmer, we don't have to worry about whether or not this guy is previously included in one of these other possibly 200 include statements up here.
Right.
All we can say is, I know I'm using Q here, so I'm going to need to include it here. So, you know, make sure it's included one way or another.
Okay.
All right, so it looked like my concatenation of my operators was a little sketch here. So it did not like, didn't like this piece. Let's prove it real quick. Yeah, so that got me the individual pieces. It doesn't like how I'm putting my operators in there. So I'm putting my operator in there by saying this. I suggested that maybe I don't need to actually concatenate it. Yeah, it definitely needs to be concatenated, or actually using our, what was it called? Two-string. That function. So those operators is giving me the integer version of those operators. So I think that almost worked. So do I need to tell it that that guy's a char? No. Asset bucket I is my operator. I want to enqueue that operator. So the way I thought about doing that is by just taking the empty string and converting that guy to that. Is there a char to string? Because it's treating it as a int.
Have you tried using the system and basically using the S and putting it into the temp and then sending the temp back to the list? Because that was what worked for me.
Well, if I do, oh, you're saying this. You're saying 0 temp, set temp equal to that, and then say temp is equal to temp concatenated with S at bucket I, then in Q temp, and then 0 out temp again.
Yeah, that's what worked for me.
Yeah. Now the question is why does concatenation work that way? I mean, this could be just as easily accomplished using a, I mean, what we're doing here, I'm saying empty string concatenated with this guy. Oh, you know what? I bet you I can accomplish it this way. Let me just try something. Can I say a string version of the empty string concatenated with S at bucket I? Let's see if that works, and then I'll explain why. Yeah. Okay. So let me get rid of this. This is kind of how the hack works with C++, but it's a good example. Okay, so let's talk about this. I'm going to take the string part off here for a second. This guy right here, double quote, this has existed since the beginning of C++. This is the string literal type, not to be confused with this much more modern string guy here. This is from C++ 11 on. That standard included a type for strings. So this is shorthand for a character array. So I was trying to take a character array, and we've seen that chars are actually stored as integers. We talked about that in 200, where The char primitive type is Java is a 16-bit unsigned integer holding 65,536 unique unique numbers that correspond to the characters on the Unicode character set. In C++, the char type is 8 bits, corresponding to the ASCII character set. So when I say something like A, B, C, this is creating this guy right here, forget about the string before it, is giving me a character array that has the byte A at the beginning, the integer equivalent, the ASCII version of that, the byte B at the second one, and the byte C at the third one. Now, if I want to use concatenation, which does not exist prior to, which does not exist with the plus sign prior to the string type here, if I want to use this guy, I need to make sure that I flag the string that's on the left as being this new modern type of string. So I'm using typecasting. So I'm saying, make sure you treat this guy as one of these guys, a string. Then I should be able to add, through concatenation, a character onto it. Does that make sense? So there's our queue with all of our operators in it. Okay, so now we have that. Let's go ahead and let's build our stack. So that's the current, I think that's the answer to the homework. Does that look correct? All right, so let's go ahead and let's build our stack. So stacks are also going to work with our same kind of node. So I don't need to actually redefine node. A node is still something that has a string in it. So I'm just going to create a stack HPP. Okay, and what if and def stack HPP, then define stack HPP, and diff here at the bottom. Then we'll build our sandwich. So for stack, we're going to have a class called stack. And inside of our class called stack, we're going to have a private section. And this guy is going to have a node pointer, and we'll call this guy top, the top of the stack. So we need to include node.hpp. Why is this guy not happy? And if, oh, there we go. I just had to save it. All right, so we're going to have the top of the stack. We'll go ahead and give ourselves a count too. You never know when we're going to need access to our count. Technically in Q, we never gave ourselves a way of getting the count. We have this private variable called count, but we never actually gave ourselves a way to get the count. So let's just add that real quick. So I'm back in Q here. Because this guy's private, I can't get him directly. So I'll just give myself a get count, and this guy will return this count. And I'll actually go ahead and steal this guy and use him. Well, I'll actually probably just rewrite it because I'm not far enough into node yet, or stack yet. So stack is going to have a top. It's going to have a count. And then the public functions will be push, pop, peek. So push is going to be void push, and this guy will take in a string as a parameter. Void, string top will take no parameters and return a string. String peak will take no parameters and return a string. So these are the three functions we want to write inside of stack.cpp. And we need to include stack HPP. And then each one of these will have the stack : before it. All right, and then also inside of stack, we'll go ahead and give ourselves the ability to get count, even if we don't use it right now. Okay. And this guy will just return this count. Peak will return this top get payload, but it's only going to do that if this top is a thing. Otherwise, peak is not going to return anything. So we can have it do a return null value, something like that. Top should actually, it's going to be pretty similar to what we have in here, but it's actually going to remove the element from the list. So if top's a thing, we're going to go ahead and say node pointer temp is equal to this top. And then, just get rid of this for a second. So I'm going to remember where that is. And now I'm going to update top. So this top is equal to this top get next node. And then I'll go ahead and say, so again, if we're trying to clean up our own mess here, we'll say string payload to return is equal to temp get payload. Then we'll say delete temp. Then we'll return payload to return. Because pop actually removes the top of the stack, whereas peak just shows us the top of the stack. But both of these guys are going to return a string. All right, push. This guy's going to put something onto the top of the stack. So if this top, if it's a thing, then we'll go ahead and say, well, either way, we're going to have to create a new node. So we'll have a node pointer n is equal to a new node passing at s. If top is a thing, what am I going to do? I'm going to say n set next node to top, to this top, and then this top is equal to n. So make n point to the same thing that top, actually, sorry, get next node. So make n point to the same place that top currently points to, then update top to point to n. Otherwise, if we currently have the empty stack. We'll just say this top is equal to n. This count plus plus in either case. So to push something on, we're going to create a new node. If there's already something in the stack, we'll make the new guy that we're pushing onto the top of the stack point to the same place the current top points to, and then we'll update the top to point to the new guy. Otherwise, we had an empty stack before, so the new top is the new guy. Either way, our count goes up by 1. All right, now we need to give ourselves a constructor for our stack.
I have a question.
Go ahead.
So when you're using get next node in a stack, is it referring to the node that's underneath it or the node that's on top of it?
It's the node that's next in the list, because we're using the same nodes as we used in queues. So a node knows about who his next node is. What next node means is going to be up to how we set the list up. So in a stack, if we're looking at a particular node in a stack, internally in our implementation of the stack, we still have nodes linked together using linked list style stuff, even though we're only using the add front and remove front. But when we are working with a node knows how to get the node it's linked to. That's the next node. So in a stack, if we have top being a node, the next node would be the node that lives below him in the stack, because that's how stacks are put together. We decided that. That's not the word stack didn't make that magically work. We're the ones who decided that when we construct stacks, we always add something above the previous guy. So that's what we did right here. Let me just grab my constructor here real quick. Where's my stack? So that's what we decided right here inside of when we pushed something on here, we created a new node, and we made this new node be on top of the current top of the stack. That's how we set it up. So we're setting our brand new node that currently points nowhere to now point to, hold on a second, this is incorrect.
Yeah, so it shouldn't just be this dot top.
Yeah.
Okay.
He points to top. So set next node is going to be the current top, and then update the current top to be your new guy who's now on top. Otherwise, set top to the new guy. So actually, this code happens either way. So we could just do this. So if there's currently a top, set this guy's next node to top. Regardless, set top equal to this guy in increment count. Then we'll have our stack. And the constructor for stack should go ahead and initialize stuff. So we'll have this top equal nothing, this count equals 0, and that's all we need for stacks. Stacks don't need to keep track of the tail because they're always working off of the top. All right, so there is our stack data structure. Let me just real quickly give us a display to prove our stack. So we'll have a void display. And we'll display it by just walking through it just like before. So, because we don't want to destroy our stack. So node pointer per node equals this top. And then we'll say for, or let's just say while kernode is a thing, we'll do a cout cur node get payload. Cur node is equal to his own next node. And at the end, we'll kick /n. So now inside of driver, we should be able to test our stack real quick. So for int I is equal to 0, I is less than 10, I plus plus. Give myself a quick stack. I'm just about done here. Stack S, stack pointer. S is equal to new stack. I need to include stack HPP. Each time through, I'll say SS push. Oh, I already have call this guy my stack. My stack push will have the string version of the empty string concatenated with. I really do think I should be able to say I like that. Now that I'm, oh, I guess not. String of I. And then I'll go ahead and tell my stack to display himself.
Did you just assume the stack's gender?
I might have. Why can't I type here? Oh, hold on. I'm in where am I? That window is not working anymore. Plus star.cpp. Give me a warning. Okay. So there's my stack 987654321 with each thing pushed on top of the other one. All right, so our stack is now working. So for Tuesday, now that we have a stack and now that we have a queue, implement shunting yards so far as it fills up the output queue with the correct code. Let's see. Yeah, I think that's reasonable. And then on Tuesday, if you want to challenge yourself, actually do the math in the end. But on Tuesday, what we'll do in class is we'll write the math portion of it as well after we implement that. So for Tuesday, your goal is to create the appropriate output queue by performing the shunting yard algorithm for processing the input queue, putting the correct things onto the output queue versus putting the correct things onto the op stack, and making sure you play by the correct op stack rules. All right, questions about that?
So do you want it to all be compiled at the end so it's like in order? Are we going to have two different stacks, like one with the numbers and one with like the ops? Like how do you want it to basically
there's only one stack.
You want it to be the step before you do the math, basically?
Correct. Go all the way up to, but not including the math. And if you want to challenge yourself, do the math. The math isn't hard, but let's play with our stacks and our queues right now doing shunting yard. So I'll tell you to focus on that. So the official homework for Tuesday is do everything up to, but not including the actual final math. But if you want to challenge yourself, do the math.
All right, sounds good.
All right, and I'll get rid of this warning real quick. I just have an extra semicolon. And then I'll push the code and I'll put the assignment up. Questions, comments, concerns, bribes? All right, I will see everybody on Tuesday. I think we're going to end up, well, actually, I have class until, I don't know if we're going to watch the next episode of Tiger King tonight or not. My class will probably be over by 9. So let's say yes, probably 9 o'clock Tiger King in the bar and grill. I'll update on Slack as my grad class is coming to an end.